known for a while that there could be a problem with our biodiversity data. Sepkoski originally assembled his biodiversity records by, as he put it, spending 10 years in the library. He recorded the origination and extinction times for thousands of species, initially using the Treatise on Invertebrate Paleontology, and then going to the primary literature of species descriptions. But at least at first he had little constraint on how good the data were, or whether there might be underlying biases that give us a skewed view of the biodiversity of the last 500 million years. We've known since the 1960s, for example, that the amount of exposed rock increases through geologic time. Most superficial rocks are young, and as we go back in time, older rocks become less and less well exposed, and therefore more inaccessible to fossil collecting. So when Sepkoski found there were many more species in the Cenozoic than in the Paleozoic, it could just be that we have a better fossil record of more recent times, because there are more fossils to be had. It also turns out that there's more paleontologists studying the near recent than deep time, so we may also have more Cenozoic fossil discoveries than Paleozoic ones. Still, another factor is that we undoubtedly know modern biodiversity much better than at any other time in Earth history. Dave Raup called this the pull of the recent. Our knowledge of modern ecology, genetics, and soft anatomy allows us to see modern diversity much more clearly than is possible for fossil organisms. After all, we know most fossil groups mainly from skeletal material, which carry far less ecological and taxonomic information than living organisms. All these factors could mean that our lovely speculation about the Earth being saturated, or not, could just be the result of how much rock, or fossils, or paleontologist effort is put towards the study of Earth's past biodiversity. Once again, we have to be careful to evaluate the null hypothesis, in this case that our lovely biodiversity patterns are just artifacts of things having nothing to do with evolution. We can get around some of these biases by standardizing our sampling of past biodiversity. How to overcome biases? Well, first we assemble lists of species found in a rock exposure. Then we look at additional exposures and count the number of new species we find as we add data from each additional fossil list. Naturally, as we add more fossil lists, that is, localities where fossils are found, the number of species grows. Eventually, if you have enough locality lists, the discovery rate of new species begins to fall off. At this point, we are close to identifying the large majority of species out there. If we add more fossil localities, we just find more species we already counted in lists from other places. This growing number of species, and eventually the plateau of our biodiversity estimate, is called a collector's curve, and the method is called a rarefaction analysis. In the diagram, we see three collector's curves for species in the Ordovician, in black, Carboniferous, in red, and Cenozoic, in green. The vertical axis is the number of genera, and the horizontal axis is the number of samples, or fossil lists, used in the analysis. Note that as species counts increase, all the curves start to flatten out, but none of them is flattened completely. We have the most complete data for the Carboniferous, since that is flattened out the most. Our count of Carboniferous species is starting to get to the point where additional fossil lists do not return a whole lot of new species. In contrast, there are more species in the Cenozoic than in the other two time periods, but the Cenozoic curve is still climbing fairly steeply, suggesting we have much undiscovered diversity in this time period. At this point, we can standardize our counts to estimate total biodiversity in each time period. First, we could set a standard number of lists and extrapolate the curves to that number to get an estimate of relative biodiversity. Alternatively, we could fit growth curves to each of the data sets and find the point at which those curves flatten out. This should be a good estimate of the total biodiversity in that time period. When we make collector's curves for each period of the Phanerozoic, we find an overall curve giving us an estimate of Phanerozoic animal diversity in the oceans. Phanerozoic diversity seems to have risen sharply in the Cambrian or Ordovician, and then starts to oscillate between a series of highs and intervening lows. Remarkably, the apparent Mesozoic Cenozoic high in marine generic diversity that was found by Sepkoski, for example, is not dramatically higher in this analysis than the Devonian and the Permian. Now, bear in mind that this conclusion stands for marine biodiversity. It appears that marine biodiversity may be pretty close to saturation and density dependence, even today. But there have been large increases in terrestrial biodiversity, and this has presumably increased overall standing biodiversity on Earth, particularly given the radiation of insects and flowering plants in the Cretaceous. The radiations of animals and plants on land effectively added a new log, in Darwin's wedge analogy, to Earth's biodiversity. These observations raise the question again of whether there is a carrying capacity for Earth. What sets the level at which density-dependent growth maxes out? We'll look at that one next.